In the last video, we introduced the fundamental theorem of calculus, and specifically we talked about part 2. Now, in part 1, we actually it's defined a little. The first part's a little different than the first one, or the second part. Um, so we actually have a condition that f is continuous, and g is defined in terms of an integral. So g is the integral from a to x of f of t dt. Now here t is kind of what we call a dummy variable because under integration it goes away and we get out the variable x instead. So we say g is a function of x. Okay, and so as g is the antiderivative of f, i.e. It is defined in terms of an integral, if we actually differentiate g, so apply a derivative on both sides, we'll just get out the f of x function. So we'll actually substitute in the upper bound. Technically here, to the rule doesn't imply it or doesn't state it, but it'd be a times 1 by the chain rule because we'd have to do the derivative of the upper bound 2. The derivative of x is just 1. And then it would be normally minus the derivative of or whatever you get at a, but a is a constant, so it all just drops out. So the derivative is just g prime is equal to f of x times 1. So now we're going to introduce kind of an applied or an application of this, and that's called the accumulation function. So again, the accumulation function gives the area under the graph from a to x, and so it's defined as capital A of x from lower a to upper x of some function. So as an example here, we have a bacteria colony whose population is described by this equation. We want to determine the number of bacteria present after 6 hours and model a rate of change for the rate of change of the bacteria colony. So let's start with the p of 6. So it's asking, well, x is time in hours, so x is just 6. So we want to find p of 6. This is equal to the integral from 0 to 6 of 2 over t minus sine of 4t dt. And so now I need to determine the antiderivative. Well, this is going to be 2 natural log of the absolute value of x. Again, just because we don't know x is positive or negative. Here, it's positive, so we could technically drop it. And then now the derivative of sine is the derivative of cosine, but cosine, remember when you differentiate it, ends up being positive, so we have cosine 4t, and then remember by the chain rule we'd actually end up with a 4 being multiplied to this value, so we have to actually divide by that. Okay, and I need to evaluate this from 0 to 6. Now, funny thing, at 0, what happens to the natural log? Well, it's undefined actually. So actually let's change this from 1. Let's start at 1, just to make this a little nicer. Alright, so going through the fundamental theorem of calculus part 2, I can actually evaluate this. So I get 2 natural log of x, or natural log of 6, plus cosine of 4 times 6 is 24, all over 4, minus, and then I'll have a 2 natural log of 1 plus cosine of 4 all over 4. And so when I did this arithmetic, I got 3.85, and then this would be million bacteria. Okay. Straightforward application of the fundamental theorem of calculus part 2, and now if I want to determine the rate of change in the bacteria colony, that's actually asking for p prime. So what is p prime of x? Well, here's my function p, and now I'm going to use the first part of the fundamental theorem of calculus to just say that it is going to be, well, I have to take whatever my function is here and input the upper bound. So it'll be 2 over x minus sine of 4x. Okay, and then all this would be times 1, but I'm not going to write that. And the 1 would come from the derivative of whatever my upper bound is. Okay, so fairly straightforward. Another application that is discussed in this section, it's not necessarily using fundamental theorem of calculus part 1, but it does use the fundamental theorem of calculus part 2. So if we have a continuous function on a closed interval, we call the average value of f to be, or the average value of f over this interval is called is this. So it's 1 over the difference in the upper bounds, and then just times the integral, the definite integral from a to b of the function. So for example, heartbeats oscillate periodically due to activity level. So for a particular person, their heartbeats at, and this hours might be a little much, but we'll leave it in hours for now. It can be modeled as this. So we want to determine the average number of heartbeats from t is 0 to t is 8. So h average, this is equal to 1 over, and then the difference in time, so 8 minus 0, integral from 0 to 8 of 130 plus 15 cosine of pi t over 6 dt. Okay, so I can go ahead and just continue working through this. So 1 over 8, and now fundamental theorem of calculus says that this is 130t plus, and the cosine is the derivative of sine, and I leave the 15 out front. The inside doesn't change, and then remember I also have to divide this by pi over 6, and I evaluate all this at 0 and 8. Okay, and I'm going to go ahead and skip the computation, or writing out the computation. But when you do that computation, I got about 126.8 heartbeats. So this means, on average, the average number of heartbeats over this time period is 126.8, or we can just say maybe 127 would be okay too. So, basic idea of this section was, or of this video, is fundamental theorem of calculus says that if you have a function defined in terms of an integral and you want to know the rate of change of that function, it's just equal to the function but with the upper bound substituted in, again due to differentiation. Okay, and then we studied the accumulation function and the average value of a function as sort of applications or extensions of these ideas.